Good morning. It is, thank God, it's Friday, this long 3-day week. Well, actually, it's like a 2.5-day week. Still glad it's Friday. Today, we want to just kind of, this problem here, number 51, is just kind of a review. For those of you at home, we started off doing problem number 51. So I recommend on page 664 that you do that problem before you continue on in this video. All right, so we're going to talk about calculating equilibrium concentrations given the value of Kc or Kp. That's what we did yesterday. So this is just kind of a review of that. Then today we need to talk about how we can introduce gas laws. I want to do a couple of practice problems with gas laws with equilibrium. Just a little trick that you need to be able to use C to be able to solve the problem. Then we need to talk about this thing called the reaction quotient Q. And I think yesterday we touched on a problem that needed that, just to be able to tell if we just mix a whole bunch of stuff together, what direction does the reaction have to go to get to equilibrium? And so we're going to calculate Q, but it's going to, Q is E, it's just like exactly like K, but we'll just do some practice problems with that. And then when we're finished with that, and we touch briefly on the Chatelier's principle, then we are pretty much finished with the chapter 15 part. Then we're going to jump into 17. I'm still hoping that we can be done and ready for a test by next Friday, although we do need to do a lab as well with this. So I'm trying to catch up from the days missed and try and stay on schedule so we can have as much time to review at the end as possible. Okay, so 51. Do we feel pretty good about it? You have 2 NO going to N2 plus O2. Okay? And it says that if the initial concentration, what does it say, of NO is 2.175? Is that what it says? Just shift that off. So my initial concentration here is 0.175 molar. 0 and 0 here. Change equilibrium. They don't give me an equilibrium concentration, but I know what Kc is 2400. So what's my change going to be?
0.1x
minus 2x plus x and plus x, right? So then I can be 0.175 minus 2x, x, and x. Okay? So Kc 2400 is equal to products x times x over 0.175 minus 2x squared. So how do I simplify that? Square root of both sides. So then it's going to be the square root of 2400 is going to equal x over 0.175 minus 2x. Then it's just algebra using the distributive property. And so x turns out to equal what?
8.573 minus, like, what it actually equals, or like what?
What does x, its final answer for x equal?
0.0866.
0.0866 molar. We good with that? So then how would I get the equilibrium over the NO? You just plug it into this, 0.175 minus 2 times that. And what does that number, so this is the concentration of N2 and the concentration of O2. So the concentration of the NO, what does it end up equaling when you plug that into here? 0.0018. Okay? So that's a classic example of this type of problem. Okay? If you want to practice another one, 52 is just like it, and I think 53 is just like it. 53 does it in terms of pressure instead of concentration. Okay? 53, the answer will be in the back of the book if you wanted to do extra practice if you feel the need for that. Okay? So, up to this point, we should be able to calculate K given concentration data, either all the equilibrium concentrations, an initial concentration and one final equilibrium concentration, or an initial concentration and a percent reactive. And then going the other way, we're given Kc and an initial concentration, and then using the ice tables, we just go through and we can solve for equilibrium concentrations all the way around. Okay, that's what we should be able to do for now. Are we all comfortable with that? Not too bad so far? All right, let me show you one little trick then. Let's look at, on this packet, 1983, the very first question. So we have SO2, Cl2 going to, what is it, SO2 plus CO2? SO2 plus Cl2. Yes. So is this a homogeneous or heterogeneous equilibrium? Homogeneous, all the same state. Okay? The decomposition is endothermic. A sample of so many grams is placed into an evacuated 1 liter bulb and the temperature is raised to 375. Okay? So I have a gas. I haven't looked at this since last year, so I'm really not really quite sure what the questions are going to ask. Okay? But I'm looking and I see grams of a gas, I see volume, and I see temperature. So immediately I'm going to be thinking at some point in this problem I'm going to have to use PV equals nRT. Okay? That just needs to be, just a correlation, a ding, ding, ding. I don't know, I'm just trying to point out when you're reading a problem what to look for. And there it is, right in the middle. What would be the pressure in atmospheres in the bulb with no dissociation? So this is how they introduce PV equals nRT. So pressure is going to equal N. How do I get N? Grams over molar mass. So it's going to be 3.509 grams divided by the molar mass. Somebody add these numbers together. Well, that's 64 plus 71. 64 plus 71 is 135. Over 135 grams per mole. Times R, 0.0821. Times the temperature. What temperature is it? 375 K. Over the volume, we like that over 1 liter, so we don't really even have to divide by the volume. So somebody do that out, and let's just get an answer there. This is just, again, classic how they throw gas laws in there. It's B that I really want to focus on. Right, you got an answer?
0.800.
Okay, and that's going to be atmospheres. Okay, but we have to have that number in order to be able to do B. Because then it says when the system has come to equilibrium, the total pressure in the bulb is found to be 1.43 atmospheres. Okay? Now, when it comes to equilibrium, what is causing that pressure? What substances are causing that pressure? All three of them, right? Because it's going to equilibrium, not all of this reacts. So we're going to have some of this, and some of that all in there, right? Get them all three. So my total pressure is equal to the pressure of the SO2-Cl2 plus the pressure of the SO2 plus the partial pressure of the Cl2. Whose law is that, by the way? That's Dalton's law. Dalton's law of partial pressures. In other words, when you have a mixture of gases, the total pressure is the sum of all the individual partial pressures. The gases all act independently of one another. They're going to exert the pressure. Whether they remember, pressure is the result of collisions with the container wall. So the more molecules of gas you have, the more collisions there are going to be, the more pressure there's going to be. So that's why pressure in moles. So, okay, if I want to go through, calculate the partial pressures, I know that Kp is given as, do they give me Kp? No, that's what I have to find out. So in order to be able to find out Kp, I have to know these three things. Okay, so my question on the next one is going to be this. So I need to know, the question here is asking, how do I get these three? Well, I know, and I didn't leave enough space here, but I know that my initial pressure right now is 0.8 molar. Pardon me, atmospheres. Sorry, atmosphere. That's what we just calculated right here. I have 0 and 0 of this. So what's my change going to be? Minus x plus x plus x, right? Now, if this happened to be a 2 out in front of here, what would we say? Plus 2x, okay? Now, I know this, and the trick on this, and the key word, this is what you underline, the total pressure is. That's telling me that I need to do this. So what can I put in? The total pressure is 1.43 atmospheres. Okay? So what's the pressure of the SO2-Cl2 going to be? 0.8 minus x. And then plus x, right? Notice one of these x's are going to cancel out. Therefore, we're going to end up with 1.43 minus 0.8 is going to be 0.63 is equal to x, which is equal to the pressure of my SO2, which is equal to the pressure of my Cl2. What's the pressure of the SO2-Cl2 going to be? It's going to be 0.8 minus the 0.63, which is going to equal the 0.17 atmosphere. So this problem is not hard mathematically, but knowing this trick right here is the key to solving it. So when they give you the total pressure at equilibrium, you have to realize, okay, Dalton's law, what gases are making that pressure? Now again, only gases exert the pressure. If it's a solid or liquid, it wouldn't be part of it. You wouldn't have to have an X for that, okay? Only the gases are going to exert the pressure. So when we have total pressure, it goes from there. So now here, give the expression for the equilibrium constant Kp or Kc. Well, we have Kp, we have all of our pressures. Now we just plug in and we get the value of Kp. I would never do this in terms of Kc. That's just way more work to have to find the concentrations on these. All right? Now, if the temperature were raised, now this is, the D is really Le Chatelier's principle, but if it's an endothermic reaction, where is heat in my equation? Left or right? Reactant or product? The left, right? If it's an endothermic reaction, you add heat to make the reaction occur. It's on the left. Okay, you can't forget the thermo. So what do you think, if you raise it from 375 to 500, is that going to push it more left to right or right to left? Think back to Chemistry 1, Le Chatelier's principle. It's going to go more left to right because it shifts in a way to use up what you're adding. Shifts away from whatever you're doing. Okay, and we're going to talk about that more in the utopian world today, but more likely Monday. Okay? as far as how to deal with Le Chatelier's principle and the stresses. But this is a Le Chatelier's principle question strictly, no math. It's just when you put a stress on the system shifts to relieve the stress. Adding heat always favors the endothermic reaction. All right, but this is what I wanted you to see. The total pressure in the bulb was found to be. So, we turn the page, as Bob Sear said. To 1992. Solid sodium hydrogen carbonate. Does anybody know the common name of solid sodium hydrogen carbonate?
Baking soda.
Baking soda. That's sodium bicarbonate. The hydrogen is the bi. Okay? So you put 100 grams. Now notice this is a solid. Making a solid and a gas and a gas. So you have 100 grams. You put it in there. Was placed in a previously evacuated 5-liter container, heated to 160. Some of the original solid remained. Okay, what is the significance of that statement? If some of the solid remained, did the reaction go to completion? No. Means we're in equilibrium. Okay, so I would maybe underline that. Some of the solid remains, that's an indicator that that's equilibrium. Okay, again, everything in these problems is going to show you a little something. It has meaning. So, some of the solid remains, and the total pressure again, the total pressure is 7.76. Well, what's the only thing that's going to be exerting pressure on this one? What gases? The H2O and the CO2. So all of the pressure, that's 7.76 atmospheres, is due to the H2O and the CO2. Calculate the number of moles of H2O gas present in equilibrium and how many grams of the original solid. So we end up having a stoichiometry problem. Okay? So it says, calculate the number of moles of H2O present. So, how many atmospheres? Okay, again, I have a temperature, I have a volume. So how do I find moles? Ideal gas law. N is going to equal PV over RT. Well, what's the pressure of the hydrogen gas going to be? The total pressure is 7.76. It's going to be half. Because for every one of these, one of those is formed. So we have equal amounts of the gases being produced because we had 0 to start with. So as this decomposes, for every one of these, you get one of those. Which means the equal pressures, because equal moles equal pressures. So I know then that it's going to be 776 divided by 2, which is 3.38. 3.88, that's right, that would have been 6. 3.88 atmospheres. The volume is given as 5 liters. Divided by 0.0821. And then the temperature is given as 160 plus 273, 373, 433. 160 and 273. 433. Advice, give me the head shake, yes. Okay? So we plug all that in and we get moles of water. Again, gas laws are, this is PV equals nRT. Whenever we have a temperature, a pressure, a volume, you're gonna use PV equals nRT. This is how they throw it in there. What do we get? 0.546 moles. Okay? So now how many grams of the original solid remain in the container in the conditions described? How do we do that? Okay, talk me through it.
You do the mole ratio from water to baking soda, use the molar mass and how many grams you start out with.
Okay, so it's going to be 2 moles of the baking soda for every 1 mole of water. And then do what?
The molar mass of
The molar mass of sodium bicarbonate, which is going to be 16 times 3 is 48, plus 12 is equal to 60, plus 1 is 61, plus 23 is 84. What do we get?
Please start out with 100. Get the
Well, I'm just, what do we get on this? You're absolutely right, you're jumping ahead. 91.73 grams of baking soda. But what is that? Somebody other than Reagan. Reagan already figured it out.
How much do you use?
That's the amount used. So now remember, excess, to find excess, you always find the amount used and then subtract from the amount given. So left equals 100 minus 91.73 grams, which is going to equal 8.27 grams left over. All right? So, again, this was more intuitively obvious, but the total pressure is only due to the gases, and because it's 1-to-1, that means that the pressure of each one is going to be half of the total pressure. So you just use Dalton's law again. Anytime it gives you the total pressure, think about what gases are making that pressure, and then just know that whatever the ratio is here, that's going to be the ratio of the pressure, because the partial pressure is dependent upon the total number of moles, or the mole fraction of each gas present. Okay? So if this happened to be a 2 and a 1, it would have been 2x and 1x, so it would have been, 2/3 of that would have been the water, and 1/3 would have been the CO2. Okay, you with me on that? Now here's a good equilibrium question. Okay? So write the equilibrium expression. We can do this. Well, what's the only equilibrium expression going to be on this one? That's right. It's going to be, we want Kp. It's going to equal the pressure of the H2O times the pressure of the CO2. Because remember, we ignore solids and liquids in the equilibrium expression. So write the equilibrium expression and calculate its value. Well, it's going to be what? 0.388 squared. So this is the hard part here. And let's just say you can't do A and B, at least write the equilibrium expression on C. And say, if I knew what the pressures were, I'd plug them in here, and this is how I'd find Kp. And you at least get, it might be a 2-point question, you might be able to get 1 point out of it. And what does that number come out to?
Well, it should be 3.88. And then it'd be 15.1.
3.88?
Yeah.
Good. Man, I tell you what, the bread is really beginning to mold. And you guys always just let it go, and then we get all these things, and then you tell me at the end. When I screw up, you got to tell me right off the bat. It's been a lot lately. All right, what do we get? 15.1. Now the unit would be atmosphere squared, but we're not worried about units. All right, so D. If 110 grams of solid sodium bicarbonate had placed at in the 5-liter container and heated to 160, same temperature, what would the total pressure have been at equilibrium? Did the temperature change?
No.
So did the value of K change? So what would happen to the total pressure? It's going to stay the same. Okay? It's going to stay the same. That just means instead of having 8.27 grams left over, we're going to have 18.27 grams left over. Because some of the solid remains. So not all of it reacts. So at the given temperature, the same amount, this gas right here cannot exceed this number. At equilibrium, it's going to be 15.1. We didn't change the temperature. Therefore, this has to stay the same. The pressures have to stay the same. You're just going to have more sitting at the bottom. Ben.
So, did we ever get a number for the pressure, or would you just say they stay the same?
You would just say they would stay the same, but we know the pressure is 3.88 for each one.
I say you just have this.
Yeah, the total pressure would be the same, 7.76.
Oh, okay. It was in the problem.
All right? Let's look at a different way that same type of question is asked. PCl5 decomposes into PCl3 plus Cl2. The PCl5 decomposes according to the equation above. A pure sample is placed in a rigid 1-liter container. The initial pressure of the PCl5 is 1 atmosphere. Temperature is held constant until PCl5 reaches equilibrium with its decomposition products. The figures below show the initial and equilibrium. So again, I start with 1 atmosphere. Okay, that's kind of like on the previous problem when we had to calculate, use ideal gas law to figure out what the initial pressure was, the 0.8 atmosphere. And now I'm at equilibrium, and here's my total pressure is going to be this. So what am I going to have to do in order to be able to find my value of Kp and all those things? How can I find the equilibrium pressures of each of these three? Okay, you guys are making this harder. Now this is a multiple choice question with no calculator. Okay? So I know that PCl5 is going to PCl3 plus Cl2. I know my initial pressure is what? 1. 0 and 0. What's my change going to be? Minus x, plus x, plus x. So at equilibrium, I have 1 minus x, and x. But what does all that add up to? So the total pressure is equal to 1.43, which is going to equal 1 minus x, plus x. Those cancel out. So it's going to be 1 plus x subtract, so it's going to be 0.43 atmospheres is equal to x, which is equal to the PCl, the pressure of the PCl3, plus the pressure of the Cl2.
It's 0.
Do what?
The pressure is 1.43.
Not 43.
Where am I? How is my?
You just
In the
make the
problem.
0 3. So 1.40.
Oh. Oh, I got you. I was thinking the subtraction you were saying there. I was gonna say that's pretty easy to subtract 1. How did I mess that one up? Okay, so 0.40 is the pressure of each one, and then the pressure of the PCl5 is gonna be 1 minus the 0.40 is equal to 0.60. Now, this is a whole series of questions. I actually answered the very last question on this one, okay? But if I'm here, let's just look at the questions on how they all relate to this, because this is a good question. This is off of a 2013 multiple choice. So it says, which of the following is most likely cause for the increase in pressure observed in the container? Why did it go from 1 atmosphere here to 1.40 given this equation? Why did the pressure increase? Okay? Okay, so think of your answer, A, B, C, or D, look at those. Did anything happen to the, do attractive forces have anything to do with pressure? What is true about an ideal gas and attractive forces? It has none. So A and B really is moot because we say gases have no attractive forces, as long as they're at low pressure. So, which one, C or D?
C.
Why not D? I just heard mumbles. What would change this? D. Temperature. Okay, temperature would make that true, but we're not changing the temperature, we're just putting more molecules in. Okay, so pressure and molecules directly proportional. So here, as a reaction progresses toward equilibrium, the rate of the forward reaction, okay, what happens to this rate? We have all of this to start with and none of this on the right. So what's going to eventually happen to the rate? Is it going to speed up, slow down, stay the same? Think about kinetics now. What happens to the rate of a reaction as time goes on? It slows down because we have less and less of this, right? So the forward rate slows. What's going to happen to the reverse rate? It's going to increase. When's equilibrium going to occur? When the rates are the same, right? Are they going to be 0? No, because they're going to still be going right, still be going left. So it's not. So increases until it becomes the same as the reverse. Well, the reverse hasn't even started yet, okay? Stays constant, decreases to become a constant non-zero, or decreases to become 0? Non-zero, okay? Because it's going to slow down, but then eventually they're going to equal one another. Does everybody understand? That's a good equilibrium question right there. Now here's the stoichiometry question. If the decomposition were to go to completion, what would be the total pressure? If we started with 1 atmosphere here and it all went to products, what would the pressure be? 2. Because 1 molecule is making 2 molecules, therefore the pressure doubles. But because it only went to 1.440, that means it didn't all go to completion. And then we come down to the last one here. Which of the following statements about Kp, the equilibrium constant for the reaction, is correct? Well, we don't have a calculator. But what's my equilibrium Kp? What's it going to be? It's going, this is 0.4, this is 0.4, this is 0.6, right? So it's going to be 0.4 squared over 0.6. Well, which number is going to be bigger, the numerator or the denominator? Denominator, so it's going to be less than 1. You don't have to be able to work it out, but you should be able to tell just by this ratio that it's less than 1. Okay? That makes sense? Key word again, total pressure. Total pressure is going to tell me I have to do this. Does that sinking in? That's Morse code. For total pressure, it means you're gonna have to do this. All right, let's look at one more example on this exact same multiple choice. Oh, we'll do that right after.